Identity and access management is not only a big topic in security, but also a very generic one. You're going to find various implementations and various products that claim to deal with identity and access management, from on-premises products to cloud services. And basically, it's all about managing user identities, starting with the information that actually identifies a user, such as a username, followed by the methods by which those users can authenticate. It might be passwords, it might be a private key or any kind of authentication method. Going further and dealing with the permissions that those users receive automatically after they have proven their identity, and even up to the level where we are actually keeping an eye on those users and keeping track of their actions. Which leads us to the official definition of those concepts behind identity and access management, which comes under the name of AAA, AAA. And the first bullet in this AAA is actually an I. It's not an A, it's about identification. So before moving forward to the authentication part, there's usually going to be some sort of an identification process where you provide a unique piece of information that uniquely identifies you as a user. It doesn't yet prove who you are. It doesn't yet prove that you actually own that identity, but it's the identity that you claim it belongs to you. So the identification part in this AAA process is going to be the action of you providing some sort of a username or a phone number or an email address, something that identifies you as a user. Second comes the authentication part. Now, this is the section where you have to provide some additional information that again is unique to you, but that additional information is supposed to prove that the identity that you just claimed in the identification part is true. How do you do this? Well, by providing something like a password that only you are supposed to know, or by signing something with your private key, which again should belong only to you. So that's the authentication part, sometimes written in shorthand notation as auth-an. Then comes the authorization part. This is where you are automatically assigned some privileges. So you have proven who you are, now let's see what you can do. And these privileges are going to be assigned by a centralized system, the system where you're actually delivering those credentials to, are going to receive back a set of permissions that tell you, well, you are allowed, since you are Andrew and you have just proven that you're Andrew, you're allowed to access these servers, maybe these VLANs, you're allowed to connect over the VPN, and you're allowed to, let's say, go outside and navigate on the internet, but only limited to a specific set of destinations. So any part that relates to policies and permissions gets applied right here in the authorization part. This is also the place where we differentiate between regular users and admin users, for example. Finally, the last part, which is not so much the last part as it's some sort of a continuous part, constantly monitoring the actions of the logged in users. What are they doing? What resources they're accessing, in what way, what operations, what changes, what modifications are they performing on those resources. This is the accounting part, down to the actual statistics, such as how much traffic did that user generate, how long did the login session last. That's the accounting part. So normally when we refer to AAA, we actually refer to authentication, authorization, and accounting. The identification part, well, you could theoretically consider it a separate process, but in most cases it is built into the first authentication step. Because in most cases you will be providing your identity, like your username or an email address, along with some secret credentials like a password or a private key. Also, it's worth mentioning here that the authorization part can also be a continuous process. So there might be systems where you're simply downloading a list of permissions the moment you're logged into the network, but in other implementations, perhaps every action that you perform has to go through an authorization server, and that server has to provide you with a verdict of allow or deny whether that operation that you're trying to submit is being allowed or not. For example, are you allowed to log into the company router and change the routing table? Are those commands allowed to you, even though you're probably an admin which already has access to those networking devices, but you might not be allowed to perform any kind of operations on those devices? And this is also filtered as part of the authorization part. Generally, all this authentication process applies to two large categories. We have the subjects. These are the ones that initiate the actions. You could be a subject, or even a machine or an application could be a subject. because they're also acting with a specific set of privileges, even though they're not real persons. Also, we have objects. The objects are the resources that we're interacting with. So an example policy here would be a policy that states that I, Andrew, as a subject, am allowed to make some changes, to write some files on a file server, which in case of AAA is going to be considered an object. I'm going to be the subject, this file server is going to be the object. Consequently, if you implement a policy that deals with machine-to-machine communication, such as a web server having access to a specific database, you might have a policy in there that authorizes any requests coming from that web server and permits them or denies them. For example, a web server might only have read-only access to a database, but any write operations, any insert or delete operations on that SQL database would be denied. In that case, the web server would be the subject and the database would be the object. Now, as we said before, the authentication part is the moment where you have to provide some sort of unique credentials that uniquely identify you as a user. Those credentials are sometimes called authentication factors. And of course, these credentials have to be stored somehow on the server as well, so that the server, that authentication server that evaluates your authentication request, can validate whether what you're presenting as an authentication factor is correct, is legit or not. Now, the first and the most common type of authentication factor is the simple password, which falls into the category of something that you know. Now, normally, as part of the authentication process, as we said before, because the identification part becomes part of the authentication process, you're also going to be presenting a username along with that password. In theory, at least, the username is not secret information, even though sometimes it's better to keep the username format at least secret. Because for an attacker to know how all the usernames look like inside of an organization, it's going to help him just a bit in an attempt to perhaps try to crack some passwords or even impersonate some users. So try to keep the username secret as well. And of course, you need to keep the password secret because that is something that you know and that is something that only you should know. Also in these categories, we're going to find passphrases, which are just longer passwords, usually made up of words or phrases that have the greatest advantage of being extremely easy to remember for human beings and extremely difficult to crack by brute force by machines. Also, PINs fall into this category. PINs, right? Personal identification numbers. The pins that you use to unlock your phone, the pins that you can use to unlock your Windows device, and so on. These are all something that you know. And even swipe patterns. On Android phones, they allow you to generate a swipe pattern to unlock the screen. This is also something that you know, and you provide it as an authentication factor. And finally, also in this category, this is where those verification questions fall into whenever you're trying to reset a password. You know, what's your birthplace? What's the maiden name of your mother? And any questions such as those, right? This is also something that you know. Next category of factors is the something that you have. Now, ideally, this should be something that only you have, of course. So it should be some sort of a security device. It could be a key fob. It could be a smart card. It could be a unique number generator that is available only on your keychain or only on your mobile device as an application. Those one-time password generators fall into the category of something that you have because only you can generate those numbers using your own devices. And finally, we get to the biometric factors, which is something that you are, right? We could talk here about retinal scans, fingerprints, the blood vessels in your palm, the iris scans, and so on. Everything that relates to your biological features and that can be uniquely tied to you as a person. Well, that factor can also be used as an authentication factor with the right systems, of course. Now, this category can also include some more exotic methods of authentication, such as the way a person walks, the way a person types at the keyboard, or the way a person scribbles their signature. And since the title of the slide is multi-factor authentication, well, in order to increase the security level of an authentication system, ideally you should at least consider combining two of these categories. So in order to have multi-factor authentication or two-factor authentication, right? Anything that's higher than 2 becomes multi-factor authentication. In order to have at least 2 factors, it's not enough just to have 2 factors. They also have to belong to different categories. So a combination of a password and a PIN is not multi-factor authentication, and it's not two-factor authentication. You need to combine something you know with something you have, or something you know with something that you are. Right? That's true multi-factor authentication, because if you're combining factors from the same category, you're not increasing the level of security. Then a PIN can be compromised just as easily. And most likely they're going to be compromised at the same time anyway. So there's no benefit in combining two factors that belong to the same category. On the other hand, if you're combining a password with a one-time password generator, the password that you know with the password that you need to generate, and it's valid for 30 seconds or 1 minute on your phone, well, that's a combination of something that you know and something that you have. If the password becomes compromised, well, the attacker cannot use it because it doesn't have access to your phone or to the application that generates unique codes on your phone. Now, in addition to the categories that we just talked about, we also have some authentication attributes that can be taken into consideration in a completely independent manner during the authentication process. For example, we could base our authentication decision on the actual location of the device or of the user that is attempting authentication. We could be looking at the actual geographical location by using the GPS or location services in the device if it's a mobile device, or we could be looking at the IP address that the device is using. By looking at the IP address, we could determine, first of all, if it's inside the company, in which VLAN, to which VLAN is it currently connected, so to which department does the device belong to, or we could decide whether it is currently connected over a cable or over Wi-Fi. If it's connected from the outside, is it connected over the internet? Is it connected over the VPN? So a lot of factors here just by looking at the IP address. Now, you might want to create some security policies that take this into consideration, because in some situations, any devices that are mobile and are not within company premises are more exposed to risk by default. So you might want to assign less privileges to the same device if you detect that it has connected over an insecure network. And then when that same device comes back home in your home company, in your home network, you could just provide all the necessary privileges, just like anybody else who's inside the perimeter. A very frequently used method of taking location into consideration is by looking at the country to which the IP address that you're connecting from belongs to. So you might be allowing connections as long as your employees are within the perimeter of your country, but you might be denying them, or you might be assigning less privileges if you detect that they're connecting from, I don't know, another country overseas, because different laws might apply, or perhaps they're just in a less secure location. The second one is regarding behavioral authentication. Now, again, this is not going to be an authentication factor, so we're not going to be looking at the way a person signs themselves or walks or types at the computer in order to provide them with authentication, but we could run a continuous process of analyzing that person's behavior after they have passed their 1, 2, or 3 authentication factors in the very beginning. So if after 5 or 10 minutes we determine by the way we analyze the person on CCTV, the way he walks, or the way they type at the keyboard, the way they sign themselves on a digital pad, that they don't exactly match the templates that we have in our database, we could cut their access at any moment in an attempt to mitigate a potential intrusion. User behavior can also be taken into consideration. That is different from what we just talked before, and user behavior here refers to the actions of the user after they've connected to a service, to a network, or to an application. What type of web pages do they visit every single time when they connect to an internal application, for example? What operations they usually perform when they connect to their banking website? If we're able to build such a baseline from multiple authentication attempts to learn from the user's behavior, then we could at some point identify some abnormal behavior in an attempt to mitigate impersonation or fraud. And finally, there's also an authentication method based on people who can vouch for you. I know, this doesn't really sound that secure, right? It's a someone you know authentication scheme. And this is actually implemented in real life as PGP, pretty good privacy, which relies on a so-called web of trust, where people just vouch for each other's identities without relying on a centralized infrastructure such as PKI and relying on centralized CAs to validate their identities. So it's a way in which, instead of asking a CA to validate a certificate for me, Andrew, I can just show you 10 people who can vouch for me that I'm actually Andrew. That's the way PGP works. Now, bringing the discussion back to a more technical point of view, when it comes to authenticating yourself to a computer system, it might be connection to a remote connection to a server. It might be an authentication to a VPN service. It might be an authentication to an application. In most cases, the method by which you'll be providing your credentials is going to be focused on something that you know. So in most computer-based systems, the authentication is knowledge-based. That is, you're providing a password, a passphrase, a PIN, something that you know and can immediately prove your identity. Now, at the operating system level, of course, in both Linux and Windows and macOS, and on every operating system out there, we have dedicated subsystems that deal with user authentication and login. In most cases, the identity validation based on a password is performed by checking the password against a local database of hashes. I know I've said this before a couple of times, but you're never supposed to store a user's password in clear text. What you should do is hash the user's password with your favorite hashing algorithm, store that hash in your database so that whenever a user tries to authenticate and sends you their credentials, you take that user's password, you hash it again using the same algorithm, and then you compare the hashes. That way you're never going to store the user's password, you'll never even get a chance to know the user's password, and the user's password is safe against data breaches and admin abuses even. On Windows, for example, we have different types of login methods. We have local sign-in, we have network sign-in, and also remote sign-in. Now, the local sign-in works just as described before. We have something called the Local Security Authority. That's an actual service within Windows that compares the credentials that you're sending with the hashes stored in a database. In case of Windows, that database is called the SAM database. That's the Security Accounts Manager database. For the network sign-in, it means that the credentials are not going to be validated against a local database, but against a centralized network-connected database. Now, in most networks nowadays, this service is called Kerberos, and the Kerberos is the one that deals with authentication and authorization for each and every user and each and every operation performed in a Windows domain. In older Windows systems, we had something called the NTLM, or the NT-LAN Manager service. And finally, the remote sign-in, that is also a type of network sign-in, but in case the user is farther outside the local network, it's usually designed to perform authentication over the public internet. So it's about validating the user credentials whenever they connect over a VPN or directly to some web application portal. For Linux, the identification part happens whenever a user is checked against the database within the etc password file, where all the local users are being defined, and then the user's password is being checked against the hashes stored in etc shadow, which kind of looks like this. And right here on the last line, you can see my username, followed by a hashing algorithm, a salt, right here, we talked about salts in a previous video, and then the actual hash that is stored right here in the local database, all right? Now, Kerberos is the #1 authentication system in Windows networks, and it's also the #1 single sign-on service available on Windows domains. Now, single sign-on basically means instead of requesting access to each and every resource that you need to access, as long as all these resources are within the same management and security domain, you could potentially present your credentials only once you connect to the network, and then receive some sort of a temporary pass that allows you access to all the related services within the same network. This is single sign-on. It is implemented in Windows networks through Kerberos as well. Now, Kerberos is based on 3 large components, just like the three-headed dog in Greek mythology. First, we have the principal. This is the device or the user that is requesting access to the network or to a service. So this is the one that we need to authenticate. Second, we have the key distribution setter. This is a major component of Kerberos because we're going to have a really close relationship to this one. And this is the place where we'll be presenting our credentials and where we'll be getting our permissions from. And finally, we have the application server, which is the actual resource that the principal attempts to access. So this could be, for example, a file server that is local on our network and can only be accessed by authenticated users. So the way Kerberos kind of works in a very, very, very simplified explanation, because it's actually quite complicated what's going on in the backend, goes like this. The principal sends a logon request to the key distribution center, again, which is part of the Kerberos infrastructure. That's actually what you're doing without even knowing whenever you're logging in into a domain account in Windows. Your Windows laptop contacts the key distribution center and sends a logon request that includes the user's identity, their password, and any additional factors that might be required for that user to authenticate. Now, the key distribution center is actually made up of two different sub-services. One of them is the authentication service, and the second one is the ticket granting service. And the service that actually evaluates our logon request is going to be the authentication service. But this is the first one that we're going to be talking to. Now, if the authentication service decides that it liked your logon request and it agreed with it, and you are now authenticated, then it's going to reply back to you with something called a TGT. That is a ticket granting ticket. Now, this ticket, as weird as the name sounds, doesn't provide you with access to any resources. It's just a proof that you have been authenticated to the domain, and then you can further request access to specific resources, such as the application server here on the right. So this was the authentication part. Once you get the ticket granting ticket, you can consider yourself authenticated to the Windows domain. Next up comes the authorization part. Now the principal has a ticket granting ticket. So when it tries to access the application server, the first thing it does is to go back to the key distribution center, and this time he's going to talk to the ticket granting service. Now, to this ticket granting service, the principal is going to present its ticket granting ticket, which is a proof that I am currently authenticated, I am part of this network, and the principal is also going to be providing a couple more information along with this ticket granting ticket, specifically the resource that he's trying to access, the resource that he's requesting access to, and also a timestamp and a client identifier that uniquely identifies me as a principal. So this request now heads over to the ticket granting service, and the ticket granting service is going to first perform some checks. First of all, it's going to check whether the TGT is valid, because I need to be providing a valid TGT in order to gain access to further resources. And also it's going to check things such as the timestamp and the unique identifier here to protect against replay attacks, to make sure that somebody hasn't captured this communication and is trying to replay it at a later time, to make sure that this specific request hasn't been performed sometimes in the past. Now, if the TGS agrees with the request coming from the principal, they're going to reply back to the principal with something called a service ticket. Now, this service ticket is the one that is actually going to allow the principal now access to the desired resource, such as this application server right here. So the principal now presents the service ticket to the application server, and the service ticket, of course, is encrypted. It's signed by the KDC, it's signed by the ticket granting service, and the application service can validate all this information by checking back and validating this with the KDC. And if all the parameters match and the signatures match, then the application replies back to the principal saying that you're okay now, you can just continue communicating with me and I'll be accepting your requests. So the principal gained access to the application server and to the resources behind that server. Now, the actual implementation of Kerberos is a lot more complicated than this. You can read more about it online, but I doubt that the exam is going to ask you about things in so much detail. What you should remember, though, is that the KDC works on port 88, both TCP and UDP, which is a very important piece of information, especially when you're performing network reconnaissance. If you find port 88 open, you can pretty much be sure that it's a domain controller. It's a server that performs Kerberos type of authentication. Two, I wouldn't say disadvantages of Kerberos, but two things that you should keep in mind is the fact that Kerberos by itself, the way it is designed, is sometimes a single point of failure in the network, which is even worse considering that it is also the enforcement point for single sign-on. So it holds the key to the entire kingdom. It holds the ability of every user in the network to access every resource in the network. Secondly, it is strongly dependent on correct time being set on the servers, on the KDC, and even on the client, because each and every request in there is authenticated and timestamped to protect against replay attacks, against impersonation, against brute force attacks. And by the way, the entire process that we talked about doesn't really happen every single time you need to access a single resource on the network. The authentication part, or the ticket granting ticket actually that you're receiving from the very beginning, has a default lifetime of 8 to 10 hours, which kind of resembles the workday. right? When you log in the first thing in the morning, when you go to the office and you log in into your Windows account, you receive a ticket granting ticket, which then you can reuse for the next 10 hours or so to receive access to any resource within the same domain. Of course, this all happens in the background. You never even know or even see this exchange happening between your machine and the domain controller or the Kerberos server. Now, Kerberos is complicated enough, but it works well enough. Unfortunately, it only works inside of our local network. What if we need to perform authentication and authorization for users connecting from the outside, like over a VPN connection? And one very old authentication protocol designed in the old days for dial-up connections and serial lines was called the PAP authentication method, Password Authentication Protocol. Such a simple name, such simple times. And it has an awfully simple implementation. It simply sends the username and the password in clear text, and that's it. The server validates the username and the password and tells you if you're authenticated or not. Everything in clear text. Of course, it's not being used anymore because sending things in clear text nowadays is just something that we don't do. We haven't been doing for some time. Still, there are situations where you could use a PAP authentication method if the exchange of usernames and passwords happens over an already secured line, such as over an already established VPN connection. So if the channel is already secure, go ahead, send your passwords in clear text. But we also have a better implementation called CHAP, Challenge Handshake Authentication Protocol, which this time relies on an encrypted exchange based on a challenge. Now, this challenge in the title is nothing more than just a randomly generated value. So the exchange over CHAP basically relies on you generating a random value, sending it to the other side, and the other side is going to calculate a hash from that random value and a predefined secret key or password that both of you should know. Finally, you will be sending me back your calculated hash. Then I'm going to calculate my own hash from the same value that I just generated and the same secret that we both should know. And if those hashes match, then I can authenticate you and grant you access. Now, this exchange is periodically repeated during the lifetime of a connection, so different challenges are being generated over time, even inside of an already active connection, to protect against replay attacks. Well, finally, we get to the interesting part, cracking passwords. Well, we're not exactly going to be cracking passwords, or perhaps I'll show you just a quick demo. But for now, let's just introduce a couple of concepts here. First of all, we're going to start with the concept of a plain text attack. The plain text attack basically is just password sniffing. If you detect protocols that don't employ encryption, that you manage to access a password database that stores databases in clear text, well, that's a plain text attack. Or an unencrypted attack. These passwords can be gathered from unencrypted protocols such as Telnet or HTTP or a PAP exchange, just like the one we talked about. Sometimes these passwords are even stored in application code or application scripts. Online attacks represent an attack behavior where you're actually dynamically interacting with your authentication server in an attempt to crack a password. So it's probably going to be about performing brute force or a dictionary attack, as in trying a large number of passwords until you find the right one. But you'll be doing so by interacting directly with the authentication service or with the login page. You're simply inputting as many passwords as possible until you find the right one. Now, as you can see, this approach does have a few issues. The first one being the fact that you're not going to be able to try as many passwords in a short amount of time. It's probably going to take you a huge amount of time, sometimes so long that it becomes completely impossible to perform. In general, most authentication services take some time to process your request before they reply with a positive or negative response. Even if that time is half a second or a second, the moment you decide that you need to try trillions and trillions of combinations, you then are going to realize that you simply don't have that many seconds in your life. Another disadvantage of online attacks is the fact that they are so easily detected in logs or in security events. Attempting a large number of passwords coming from the same username or the same IP address in a short amount of time is going to raise some flags, is going to raise some alarms, and most likely is going to end up in blocklisting that specific source or that specific IP address or that user who probably only had a chance of trying, 3, 5, or 10 passwords. Many authentication systems lock users out of their authentication attempts after too many failed attempts. Other authentication systems employ a sort of a back-off mechanism where each and every subsequent attempt is going to take more and more time to evaluate, or you're going to be allowed to try again after 10 seconds, 30 seconds, 1 minute, 5 minutes, and so on. It's an exponentially increasing back-off time. If you want to try this, try entering the wrong PIN multiple times in a row on your mobile phone. See what's going to happen. You're not going to be locked out completely, but at some point the phone is not going to allow you to try again immediately. You'll have to wait a certain amount of time before you can attempt the next value. Offline attacks are the ideal attacks against passwords because they rely on compromised hashed databases of passwords. Now, normally, as we said before, you shouldn't store passwords in clear text. What you should do is hash those passwords and then store those hashes. Well, if an attacker gets their hands on such a password database of hashes, then they can take this database and try to recompute all the possible entries that can generate those hashes in an attempt to find the actual passwords. Now, there are multiple ways of doing this. Password spraying is a very interesting concept and kind of reverses the brute force concept. As in, instead of choosing a username such as, I don't know, admin or Andrew, and then trying all the possible passwords in an attempt to find the password for that user, well, why not do things the other way around? Let's choose a simple password, such as password 123 or 123456 or something like that, and then try all the possible usernames in an attempt to find a valid username inside of a company that probably isn't that security conscious and is using that very simple password. Because in most cases, an attacker only needs a valid user account. It doesn't matter which user account it is, but it needs some sort of user account to get a foothold inside of that network to compromise it. Brute force attacks basically mean that you're going to try every single password until you find the right one. Even if you're doing an online attack, even if you're doing an offline attack, brute force means try everything until you succeed. It's the type of an attack that takes the longest, but it's also the type of an attack that guarantees success if you have enough time and if you have enough resources. If you don't have enough time and if you don't have enough resources, you also have dictionary attacks. Now, dictionary attacks rely on predefined word lists, simple lists in text files that include the most frequently used passwords or dictionary words, or even small combinations such as adding a couple of numbers or digits before or after that dictionary word. Sometimes this is called a hybrid attack, which combines just a bit the dictionary attack with a brute force attack. The advantage of this is that the search space is going to be much smaller. So if it takes you, I don't know, maybe 5 hours to try all the 7-character passwords out there, it's probably going to take just a couple of seconds to try all the 7-character words in such a word list. So it's much faster, but of course it doesn't guarantee success. It could be that the password that you're looking for simply is not in that dictionary file. Or if it's randomly generated, it simply cannot be defeated by a dictionary attack. What is truly dangerous against passwords stored as hashes are rainbow tables. We talked about this in a previous video. We said that rainbow tables are pre-calculated, pre-compiled databases of hashes. So it's basically a database in which somebody took the time and resources to generate all the possible hashes for all the possible inputs. Let's say, for example, every alphanumeric password from 1 up to 8 characters. Calculate them all, generate all those combinations, and then calculate the hash of that result. Store those hashes in a database, and there you have your rainbow table. Next, when an attacker gets their hands on a password database from an application or an operating system, all they need to do is now search the hashes from that database inside of this rainbow table, which takes a lot less time. Searching in a database takes a lot less time than building and actually computing that database. Now, this rainbow table approach or rainbow table attack can be mitigated by using password salting. That is, adding a unique set of characters whenever you're calculating the hash for each password. You don't even need to keep those characters, that salt, secret. It can be stored right next to the hash, in fact, or right next to the username. But this defeats the use of rainbow tables, because now the hash that gets generated is not generated from the pure password, but from the password and a small set of characters known as the salt. So if you find that hash in a rainbow table, the input corresponding to that hash is not going to be your password. It's going to be something else that has no meaning. A very well-known software used for cracking hashed passwords is called hashcat. It can be freely installed and it's freely available on Linux distributions, especially in Kali. I believe it comes pre-installed with Kali, by the way. And also, there's a website in here, I'm sure I've shown it to you before, a website that you can play with and where you can input some of your passwords. Try not to input your real passwords, perhaps, but it's still going to give you quite an interesting insight into how difficult would it be to crack a password like this, assuming a brute force attack, of course. Now, to show you how hashcat can be used, and actually there are a lot of methods in which hashcat can be used, but just to play with a couple of hashes, let's assume that this input.txt file includes some, let's say, real passwords from real users. What I'm doing here is actually I am echoing this password right here, one on every line, and I'm passing it over to the MD5 sum utility, which is going to calculate an MD5 hash of this password, right? The -n right here allows me to remove the new line at the end of echo. This tr command right here allows me to remove any white spaces and dashes from the output of MD5 sum, and then I'm going to redirect the calculated hash into this target hashes.txt file, which kind of looks like this. There you go. This is a list of MD5 hashes that correspond to these 1, 2, 3, 7 passwords. Okay, let's assume that this is a hash database that I've managed to get my hands on from a real compromised server or a web application. How can I crack these hashes now and retrieve the original passwords? Well, I have two methods of doing so. I could try perhaps brute forcing all the possible combinations that can lead me to potential passwords, all the possible character and letter and symbol combinations. Let's try this. First of all, let's have a look for just a second in the man page for hashcat. We're focusing on this built-in char sets first, because you can see that by using these switches on the left, we can choose to crack based on specific character sets like lowercase letters, uppercase letters, numbers, hexadecimal letters, symbols, or we can just combine them all in this question mark A. Question mark A actually includes lowercase, uppercase, numbers, and symbols. Right, so this is pretty much going to cover every possible symbol that can be used inside of a password. So we have this set. All right, next up we have the attack mode. What type of attack do we want to conduct with hashcat? Now we could be using a brute force, we could be using a word list, but for now we're going to be focusing on brute force. All right, finally we have the hash type. Notice that we have a lot of hash types in here. Not just the traditional MD5, SHA hashes, and so on, but we have MySQL hashes, NTLM hashes, right? PHP hashes, and so on. So what we are trying to crack right now is the first type of hash, which is a simple MD5. Now that we know these parameters, let's try building our hashcat command. All right, that's the hashcat command that we're going to be using. -A3 is the attack type. Remember, this one was brute force. -M0 is the hash type, this was MD5, -O is the output file, so whatever I manage to crack is going to be stored in this cracked password txt file. This is the target hashes that we just saw before, and this is the pattern that I'll be trying. Question mark A, 1, 2, 3, 4, 5, 6 times. Let's see how long is this going to take and if we find any passwords. I'm going to press enter here, and you can see here it actually uses discrete hardware. So if you have dedicated graphic cards or a beefier CPU that you can use, it's actually able to set them on fire, right? It even has a, I believe that's mentioned right here, temperature aboard trigger set to 90 degrees Celsius. So it is extremely CPU intensive, the process of cracking passwords. You also get some hints in here if you want to improve the cracking performance. You also, the line right here at the bottom tells us that we can periodically check for the status using the letter S. Let's press S right here. All right, so it's telling us that it's currently running an MD5 cracking operation. And this is the pattern that we've chosen. Apparently, we've already recovered 1 out of 7 hashes, which is not bad actually, right? What is kind of bad, let's run this status command one more time, is that now we've been running it for half a minute, but we still have about 2 hours left to wait. And that's just for 6 characters. Let's quit this, Let's see how long it would take us if we were to expect 7 characters. Notice we don't even know how long the passwords are, so we just have to try it. So I've added one more to the pattern in there. Let's choose status, and this time is going to take us 10 days. And I must say, this is pretty good. If 10 days seems a lot to you, this is actually pretty good because we're running on a pretty good CPU right here. It's not an old CPU, it's kind of last generation right now at the time of this recording, so it's not a bad performance, but it's going to take a while nevertheless. All right, let's quit this because we're not going to wait 10 days in here and see the end results. Right now we have a cracked password txt, and inside of it we can see that it was able to determine the simplest password out there, which was just 123456. Just a quick reminder, these were the original passwords, so it was only able to crack this password right here. Now, if we were to give it some more time, it would probably reach this password as well, and this one, and it would never be able to crack this one because we were limited to 7 characters. All right. Now, let's see if there's a better way of doing this instead of just brute forcing everything blindly. We could be using a word list or a dictionary attack. And it's actually not exactly a dictionary attack, it's more like a direct type of an attack. So we're basically just looking for those passwords in this list right here. This RAW-Q list comes embedded with many Linux distributions. Just search for it, or if not, you can just download it for free from the internet. It's just a huge TXT list of words. It might happen to include passwords, it might happen to not include all the passwords, but it's worth trying, especially because it's going to take a lot less time to validate this list. Again, the hash type that we're looking for is going to be MD5. We're going to output the results in this cracked password txt file, the same one, and we're using the same target hashes as before. So let's press enter here. Let's wait a couple of seconds and it's done. I mean, how long did this take? 2 seconds? And it estimated that it should have lasted 0 seconds. So it did have some better expectations from the CPU actually. So it did recover 4 out of 7 passwords. Now, it was not able to continue looking for passwords because it reached the end of that word list. So it did not have anything else to go on with. But it's more than enough. So let's have a look inside of this cracked passwords txt file. There we go. Now, more passwords in here. We have password, we have test1234, and we have the secret. You can see they're pretty much kind of dictionary words, right? So they're simple passwords that can be easily cracked using dictionary attacks. The other ones, let's see, the ones that we were not able to crack are the ones that actually mix lowercase and uppercase and letters or symbols in their structure. Right? But it's still a start. I mean, for 2 seconds, I would say this is a success. Right? Ideally, you should combine this dictionary attack with a little bit of brute force, and hashcat can do this in order for you to be able to, interpolate numbers between words and replace, for example, alphabet letters with numbers or symbols, like most people do in their passwords. But anyway, you do get a lot of flexibility with hashcat. Play with it. It's completely free and open source. See if you can crack some hashes on your own. Now, moving over for just a bit to the other side of the battlefield, and this time talking a bit about securing passwords. Now, whenever you think about securing passwords, start by thinking about just securing data, right? You have to think about how to secure data when it's stored, that is data at rest, and how to secure that data whenever it is in transit, whenever it is communicated to someone else. Now, when it comes to passwords, again, the same principles apply here. You have to find a way to store them long term, and you also have to find a way to securely communicate them. And I'm not here talking about sharing passwords, not about communicating them to your work colleague, but to any type of authentication system, because whenever you're logging into something, you'll have to send your credentials somehow over a potentially unsecured medium. But coming back here to our discussion about how to securely store passwords. And traditionally, password storage is a very big potential security risk, especially in a large enterprise, because if you just leave people to manage their own passwords however they want, you're going to run into situations where they start reusing the same passwords that they're using onto their personal accounts. They're going to be sharing accounts. They're going to be using very weak passwords. So there are solutions, which by the way can be software or hardware, which we call password managers. These password managers actually deal with two very important pieces of the puzzle when it comes to securing passwords. First of all, generating secure and unique passwords for each and every service that you're using, preferably completely random, without any kind of meaning. And secondly, they deal with storing these passwords in a secure, let's say, compartment. Because if we're randomly generating a 20-character alphanumeric and punctuation signs in there, perhaps password for each and every service that we're using, most likely we're not going to be remembering them all by heart. So we have to store this information somewhere. So the first method of storing these passwords would be on a physical device, such as a password key, which can be attached to your keychain, for example. It can be an actual physical USB key or an NFC device. For example, the YubiKey series from Yubico has been for quite some time one of the best integrated solutions out there regarding security keys. You also have USB and NFC variants for all these security keys. And of course, you can also use a software password manager, such as 1Password or LastPass or KeePass, which can store your passwords in an encrypted database. It can be stored in the cloud. If you don't trust the cloud, you can just store them locally, but then you'll really have to take care of that database. And in some situations, you can even combine these password vaults, software password vaults, with actual physical hardware keys. So you can have a physical key that unlocks the password vault where all your individual service passwords are stored. I personally like to use KeePass XC, which is a fork of the original KeePass. I like it because it's completely free. It doesn't tie me to any specific platform. It's completely open source, and it also integrates quite well with additional authentication factors, such as Windows Hello, or the fingerprint on a macOS laptop, or your Face ID on the iOS application. So go ahead if you want to try a completely free solution as a password manager. Just keep in mind the fact that it's not going to store your database in any cloud. You have to take care of that database and perhaps synchronize it across multiple devices if you have them. All right, now the authentication process in itself, or the authentication technologies involved in this process, are a big part in any enterprise organization. And it's not just about password management like we just talked before, but it's also about the entire authentication process, and it usually involves more than one simple factor. So we're going to talk about a few technologies that not only help us perform password management in a secure manner, but also allow us to implement multi-factor authentication in an enterprise environment. Starting, for example, with the smart card. Now, the smart card in itself, or the smart part in that card, is basically just a small cryptographic processor. So it's a card that is able to process some data. In most cases, this card is used to store the certificate of that user along with the private key that was used to generate that certificate. That's one of the reasons why these smart cards, you really have to take care of them, right? You have to guard them just like the keys to your apartment. Make sure nobody else gets their hands on that smart card, because that's also where your private key lies. And this is why you use smart cards in an enterprise environment to sign emails, perhaps even to authenticate in Kerberos, in a Windows Active Directory domain. With Kerberos, for example, you can use a smart card or the private key stored on that smart card to generate a unique ticket-granting ticket request in order for you to get access to the rest of the environment, the rest of the services in the network, which is signed, uniquely signed by you. And we all know by now that for a digital signature, you need a private key, which is stored on the smart card. Now, of course, you will need a device able to read these smart cards and be able to use the information stored on them. And because mobile devices nowadays don't really have smart card slots anymore, but we do have some smart card readers out there, well, some people thought that why not just embed everything into a simple USB device and call that USB device your actual key, right? So instead of a smart card, we have a smart USB device that does pretty much the same thing as a smart card. Stores cryptographic information, also is able to generate new cryptographic material, such as when you need to use the same private key to generate a certificate for a different purpose, like for example encrypting files, and another one for signing emails. Well, smart cards and USB keys can be stolen, can be lost, can be shared. One technology that cannot be lost, stolen, or shared is a TPM chip. This is called a Trusted Platform Module chip, which is an embedded chip into your motherboard, in your mobile device, in your laptop, even in the motherboard of your desktop PC. And it's basically a so-called secure enclave. It's a very secure area where your level of interaction is quite limited. You can treat it as a black box. For example, you can ask that black box, that TPM chip, generate a certificate for me, generate some cryptographic material, give me a randomly generated key for me to use in a secure communication. But you're not allowed to change the contents within that black box. And for, let's say, legacy apps or operating systems, you can even convince, through software, of course, you can even convince the TPM chip to present itself as a so-called virtual smart card. Because, again, it pretty much does the same thing. Now, all three so far are considered to be user devices. They're things that regular users have to interact with. Well, we also have some secure enclaves, some secure cryptographic modules that can be installed in actual servers, because servers must use cryptographic information as well, and especially those servers that act as registration authorities or certificate authorities or even root CAs. Now, for those situations, we also have some dedicated types of equipment called HSMs, hardware security modules. Now, even though the name suggests that it's a module that it's supposed to be plugged into a server, which in most cases it actually is, most HSMs are just PCI Express cards that you can plug into a PCI Express slot in your server. You can also have them as dedicated appliances, rack-mounted appliances, or even external peripheral devices connected through USB, which kind of makes them some very smart enterprise-grade USB keys. Again, we use them for the same purposes. We use them to store cryptographic information and to generate new cryptographic information, so they are really resistant to outside tampering and or attacks. And you also get a big advantage with HSMs. The fact that the actual cryptographic module is not tied to the server anymore. You can, at any moment, just remove the card from one server and insert it to another one. For example, if you need to upgrade the hardware in your company's root CA, you can simply save the same cryptographic information onto that HSM and just pop it out from the first server and plug it into the next one. Now, the authentication methods and technologies discussed so far assume that the device, the computer, is already connected to the network and the user is the last entity that needs to authenticate. But there are situations where we need to provide authentication services for users connecting to the actual network. And we have a couple of methods of reaching a network. For example, simply by plugging the network cable into our computer. We probably want to authenticate any devices that randomly happen to connect to our wired network. The same goes for wireless, of course, both for enterprise wireless networks and for guest networks as well. And we also have users connecting from a remote location. Those are going to be the users connecting to a VPN endpoint, where, of course, there has to be some sort of authentication going on. And for these situations, we have something called EAP, Extensible Authentication Protocol. Now, even though the name says protocol, it's actually a suite of protocols, a grouping of protocols, which is often known under the name of a framework. So we're going to call it the EAP framework. And this framework is actually a wrapper, some sort of an encapsulation, let's say generic encapsulation, for a multitude of authentication methods, ranging from passwords down to biometrics, or relying on user server certificates, either one or both, even authentication methods relying on the SIM card that is currently in your mobile device that is attempting to access a specific enterprise network. So it's a framework that supports a bunch of authentication methods. And while the framework sounds nice, the actual implementation has to be an actual protocol. And that protocol is 802.1x. It's an IEEE standard, as you can probably guess by the naming format. And it's a protocol that selects or establishes which authentication method is going to be used within this EAP framework. Whenever a device tries to access a network, either directly over a cable, over wireless, or over a VPN connection. And we have a couple of terms that we need to be familiar with when talking about 802.1x. The first one being supplicant. The supplicant is the actual device requesting access. Next one, we have the authenticator, which might sound a bit counterintuitive because the authenticator is the device through which you get to access the network. If it's a cable network, it's going to be the switch. If it's a wireless network, it's going to be the access point or some implementation down to the wireless LAN controller. If it's a VPN connection, of course, it's going to be the VPN endpoint that you're connecting to. So that's going to be the authenticator. That's a device that decides whether you will receive or not access to the network. And finally, we have the authentication server, or the AAA server, authentication, authorization, accounting, right? And that's the actual server located somewhere where it's supposed to be reachable by the authenticator, because on the authentication server, the actual database of the users and their hashed passwords is stored. So what happens is the supplicant sends their own authentication credentials to the authenticator, like the switch, for example. The switch then contacts the authentication server, checking whether those credentials are valid. If they are, the authenticator receives a valid response from the AAA server and then unblocks the network port, the actual network interface through which that device is attempting to access the network. And of course, if a negative response is received, then the port remains in a blocked state, allowing only authentication traffic to go through, but not any other type of data. Now, you might have noticed that in this deployment that we just explained, the actual switch or the access point or the VPN endpoint doesn't need to store the entire user database, which is great because we might have hundreds of switches and thousands of access points, right, in a large network. It wouldn't be feasible to download it and keep that database updated onto each and every network device. And it wouldn't be secure either, right? So the AAA architecture allows us to implement authentication policies at the edge of the network where users actually get to connect, and also store that database in a centralized location that everybody can reach and check whether whoever tries to access the network has valid credentials or not. And that database is going to be stored in something called a AAA server or the authentication server. And we have two large types of authentication servers nowadays, differentiated by the protocol through which we're accessing them. And those two are called Radius and TACACS+. Now, generically speaking, Radius supports PAP, CHAP, and EAP as authentication methods, but since PAP and CHAP are kind of old and not so secure anymore, pretty much everybody nowadays uses some version of EAP, some implementation of EAP. So what happens is that when your computer attempts to access the network through a switch port, for example, the communication between your computer and the switch is going to be limited to EAP over LAN traffic. That's EAP-OL. EAP over LAN traffic basically means that we're allowing any type of traffic that relates to EAP authentication. And that's the only type of traffic that we're allowing through that port for now, before the user is authenticated. Now, the switch in turn is going to encapsulate that authentication information into a Radius message, which encrypts that authentication data and then sends it to the Radius server as an access request Radius message. And that communication happens over UDP ports 1812 or 1813. Now there are going to be a few exchanges of additional messages between the AAA server and the actual supplicant, your laptop, your computer, as a couple of messages called access request or access challenge. The purpose is for your computer, your supplicant, to be able to respond to those challenges in order to demonstrate that it actually holds valid credentials, which correspond to the chosen EAP method. So if we're authenticating using certificates, you're going to have a chance to present your certificate. If we're authenticating using multi-factor authentication relying on biometric factors, then the supplicant is going to have the chance to send that biometric data down to the AAA server for verification. Finally, according to the AAA server's decision, it can reply back to the network switch with a message of access accept or access reject, depending on whether the user or the device managed to properly perform authentication. So that's the authentication and authorization part. There's also the third A, the accounting phase, which can also happen using the Radius server, that is monitoring the user activity, the login times, and any authorization request, for example, coming from that user over the entire duration of that user's connected state. And this gathering of information and accounting communication happens over the second UDP port, that's port 1813. Now, in real life, you're going to encounter Radius implementation, especially for user and device authentication requirements. There's also another requirement for AAA environments, That is when you need to manage the administrative access of your admins to your servers, your network switches, your firewalls, your routers within the network, so that each user, each admin in this case, would not only be able to access all the devices in the network using the same credentials, but they would also be able to receive different permissions or different privileges depending on the device that they're trying to connect to. Now, TACACS, on the other hand, comes with a couple of improvements. Not only it works over TCP, so the communication is more reliable, port 49 by the way, but it also encrypts the entire data, not just the authentication information like with Radius. That's simply because TACACS is mostly used with administrative accounts logging into network devices, for example. And in that case, it's not just the authentication information that is sensitive, but also the actual commands and the configuration files and the settings that are being changed in there. So that's why it's much better to have the encryption covering the entire communication, not just the authentication part. And the separation between all the AAA functions is much better established, which leads us to situations where we can even perform authorization not just for the entire user that is logging into a network switch, for example, but also for each and every command that the user submits to that switch's CLI. So we can have per command authorization. And accounting, of course, because we need to keep track of who is doing what, especially in the administrative world. Now, one-time passwords, we all know them, right? It's a type of two-factor authentication. It's a type of another factor authentication that relies on something that you have. So you need a device or a software program that generates unique codes that are unique just for you, and sometimes they're unique even depending on the current time and date. Now, this uniqueness, or whatever makes a one-time password generated unique just for you, is ensured by the fact that all these generators rely on some sort of a starting seed value. That's an initial value based on which all the subsequent unique passwords or codes are going to be generated. Now, the one-time password generated and the authentication server should be configured with the same shared secret or the same secret password, which can be delivered as a string or as a QR code. You probably saw this whenever you're enrolling in two-factor authentication. You can scan a QR code with your phone, and that becomes the seed for any subsequent passwords that are going to be generated by your app. Now, in order to provide uniqueness, the seed can be combined with a counter, which makes it an HOTP. That's a HMAC-based one-time password. And that counter, of course, is being incremented with each new password generation request. Alternatively, and this is probably the method that you're most familiar with, is the time-based one-time password generator, where the actual value of the password is generated depending on the shared secret, of course, but also on the current time of the day, down to the minute or to the second. These are the codes that in your one-time password generator app, you're going to see them as expiring in a couple of seconds. Usually they're valid for 30 seconds or 1 minute or so, just to give you enough time to enter the generated code into whatever authentication system you're logging into. And we also have some additional methods of delivering this second factor. And these methods are sometimes called out-of-band verification or two-step verification. I'm probably familiar with these because many online services ask you to validate your account, perhaps to validate your login by sending you a one-time code over email, for example, or over SMS, or even over a phone call or an automated phone call. And more recently, with applications such as Okta or Microsoft Authenticator or Duo, you can even send this request as a push notification to your mobile app, and then you need to interact with the mobile app to provide your agreement with that authentication request. Another widely used authentication technology is biometric authentication. This one takes into consideration certain features that characterize you as a human being or as a particular human being. Things such as your iris, your retina, your fingerprint, or even the way you sign yourself on paper. Now, as you can probably guess, relying solely on biometric authentication is not 100% recommended because there are a lot of potential errors or misidentifications that can happen whenever you are scanning for actual physical characteristics. It's not just comparing ones and zeros anymore like we did with passwords or one-time passwords, but now we're looking at how closely are your facial features, for example, matching what we have in your database. It's never going to be 100%, of course, so there is going to be some margin for error. So the efficiency or the reliability of a biometric authentication system is actually measured in how many errors does it produce. And we have two types of errors, and they're actually called type 1 errors and type 2 errors. The type 1 error is the false rejection error, or the false rejection rate, if we consider how often this happens. And it happens when the biometric authentication system fails to authenticate a legitimate person. It's bad, it's inconvenient, it's not exactly a security risk. So that's a type 1 error. Now the type 2 error is a bit worse from a security perspective. This is a false acceptance rate. The false acceptance rate, the FAR, indicates how often does the biometric system allow somebody who is unauthorized to gain access to the system. So it mistakenly identifies that person as a legitimate user when in fact they are not. Of course, this is a security concern because you are providing access for unauthorized people. These error rates can be corrected over time by performing some fine-tuning, and it also relies strongly on the enrollment process. That is the initial process where you're actually capturing those initial, fingerprints, your face, the shape of your face for Face ID, for example, or a retina scan. The first time you capture those details and you store them in an abstract format in a database, that is called the enrollment process. The accuracy of all the subsequent identifications performed by that biometric authentication system strongly depends on the quality of that initial material that was stored during the enrollment phase. And we also have the crossover error rate, or the equal error rate. That's the point on a graph I'm going to show you in just a second, where these two types of errors meet. So if you just perform a quick Google search by searching for false rejection rate versus false acceptance rate, and I've just clicked images here, you can see that pretty much all the graphs looks the same, right? So if you look at the first one right here on the left-hand side, on the vertical right here, we have the number of errors, and on the horizontal axis, we have the sensitivity or the level of security of that system. So the higher the level of security or sensitivity of our system, the less false acceptance events we are going to have. Consequently, the higher the level of security or sensitivity, the higher the level of false rejection events we're also going to have. So the more sensitive the system is, the more picky it becomes, up to the point where it's going to reject valid people simply because they've suffered some minor changes. Let's say, I don't know, they grew a beard from one day to the next, or or they simply positioned their finger on the fingerprint reader in a slightly changed position from the original enrollment image that the authentication system stored. So ideally, we're going to try to fine-tune the biometric system to match this crossover error rate, or the equal error rate. That's the sweet spot for a biometric system. Some of the issues that you might encounter with biometric systems, I'm sure you can think about at least a couple of them. First of all, we have reliability. How reliable is my fingerprint going to be every single time it's being read, or my retina or my face? Consider that I might be wearing glasses, maybe I'm wearing a mask, maybe I grew a beard, maybe I had a haircut. All right, so we're going to have to accept some sort of margin of error, which is going to lower the reliability of the system itself. There are also privacy concerns. Not everybody is comfortable having their physical features stored in some database. Of course, there's higher cost because those sensors, well, they cost money, and the more sensitive we want them to be and the less errors we want them to produce, of course, the cost is going to be proportionate with these requirements. And we might also encounter some accessibility issues. Not everybody might be able to use those biometric authentication systems due to some accessibility problems that they might have. So make sure that you do not discriminate anyone by forcing them to use a specific biometric authentication system. So the main types of biometric authentication systems rely on scanning fingerprints. These are the most common ones, the cheapest one to implement, and you probably can find them pretty much everywhere nowadays. Now the problem with them is that they can be fooled by either a high-resolution scan of a fingerprint or even by a mold of that fingerprint created from plastic or silicone. There are more advanced scanners, so-called palm scanners, which instead of just scanning one or two fingers, they're going to scan the entire shape of your hand and also the blood vessel positioning in your palm. Of course, the sensors are not going to be as small as with the fingerprint ones, and the entire solution cost is going to go up quite a bit. But I have seen even laptops implementing this type of palm scanning technique. Now, face recognition can be done in a number of ways. It can range from a simple image recognition of how your face looks like, or it can go up to the technology within Face ID, for example, which creates a three-dimensional model of your face, which enables the biometric system to scan your face with better accuracy, also makes it harder to fool, harder to trick using just a picture of somebody's face. We can even go deeper and scan specific features of the human eye, like the iris or the back of the retina. Both rely on features that normally do not change from birth to death, apart from some specific disease situations. But in general, the retinal scan is a bit difficult to perform because it needs to scan using an infrared light the back of your eye, while the iris is at the front, so it's much easier accessible. Of these two, which one do you think can be fooled by a high-resolution photo? That's right, the iris one. The iris scan can be fooled because it doesn't rely on any infrared scanning or three-dimensional model. It's basically just a picture of your iris. Finally, we have some more exotic measurements of biometric factors, such as the way a person walks, the way a person doesn't talks, right? Yeah, actually, even the way a person talks, right? Because that's going to be voice recognition. Even the way a person signs themselves on a paper with a pen, how they perform their actual handwritten signature. Normally, these factors, because they produce a lot of errors, are used as a, let's say, continuous authentication after the user has already been granted access. So we've identified you using your, I don't know, perhaps your fingerprint and your password, you've gained access. Now for the duration of your session, we're also going to monitor how you type on the keyboard, what's the tone of the voice that you're using, how are you signing yourself on a digital pad, for example, and if necessary, we might decide at some point that you do not match those features that we have in our database, and we might decide to cut off your connection until we actually clarify whether you are the person that has passed that authentication and identification process in the beginning. So in other words, even if you have the right credentials but you don't behave like the person that we know you should be, we might decide to take some action. All right, so a lot of stuff in this chapter, but hopefully a lot of useful and interesting stuff that you can even find around yourself every single day. All right, so thank you so much for watching. If you have any more questions, if you want to continue this discussion, please use the comment section. And if you found this informative, like and subscribe. Good luck on your studies and see you on the next video. Bye-bye.